Hello friends, welcome to this session. In this session, we are going to study the topic bending stress diagram and section modulus. So these are the two important terms we have to study in this particular video lecture. In the earlier video lecture, we gone through the flexural formula. So we know that the flexural formula m divided by I is equal to sigma by I and E upon R. So that formula you remember because that it is important for solving the further problems onto the bending stresses. So let us first of all see the bending stress diagram. So already bending stress distribution diagram we have flexural formula. So this particular formula we derived in the last video lecture. After rearranging the equation, you know this particular formula also we derived, the sigma is equal to E upon R into Y. So that all these terms you already knows, you already studied in the derivation that m is the maximum bending moment or moment of resistance, I is the moment of inertia, sigma is the stress or bending stress in the beam to resist the bending moment, y is the distance measure from the neutral axis. Whatever the top fiber or whatever the strip or whatever it is taken, the section up to its top and up to its bottom fiber, the y is the distance measure from the neutral axis, and E is the modulus of elasticity or Young's modulus, R is the radius of curvature. So that all these terms you already knows. So you just please remember all these terms. This equation shows that for a constant value of E and R, stress is directly proportional to the distance y. So this neutral axis, the distance from the neutral axis y, and this stress, the relation is stress is directly proportional to the y. Means y is the distance from the neutral axis up to the top or bottom fiber. It means that with here we have seen that this flexural formula and this stress is directly proportional to the distance of the distance of the fiber from the neutral axis, right? So next it is when it means that stress is varies linearly with distance. Whenever this distance is increases, the stress is also increases. So up to the top fiber is the maximum distance, so that up to the top fiber or bottom or top edge or bottom edge of the cross section of the beam, so there is a stress is large or maximum. That is, if you taken the y means exactly onto the neutral axis, there is a y is 0, and whenever you go from the neutral axis, there is a y is increasing. At the maximum y, will get the maximum bending stress. Okay, so if you take the y is equal to 0, then bending stress is 0. If your y is maximum, bending stress is also maximum. So that you remember here. And at the extreme fiber, extreme means at either top or bottom of this edge, there is a y is maximum. At that case, there is a maximum bending stress is exist. So there is a maximum bending stress in is also a maximum. So if you want to draw the figure, that is a bending compression and bending tension, means at the compression side or in the tension side, if you bend this particular beam, at that time there is a stresses are developed. Above the neutral axis there is a compressive stresses are developed, and below the neutral axis, so this is the neutral axis is there is a tensile stresses are developed. So the magnitude of the compressive stress, if it is there, so you just mark in the right of this line, and the tensile stress is positive on the left of this line. So we'll get this particular diagram, this is the bending stress diagram for this particular beam cross section. So in the 0, here it is, you can see there is a intersection point on the neutral axis, there is a 0 bending stress, means there is a y is 0. If you go either in the upward direction or in the downward direction, there is a stresses, bending stress is increasing. And at the extreme fiber, means at the top or at the bottom, there are stresses maximum. So this is a bending stress diagram for this. Like that, this is a rectangular cross section of the beam, this is the bending stress, and this is a channel, this is the I section of this beam whose depth is d. The bending stress diagram is like this again. So again, in the bending stress in the compressive side and bending stress in the tensile side, again here it is that 0 at the neutral axis, and maximum bending stress is at either compressive or maximum bending stress in tension in the extreme fiber, either top or bottom. So there is a maximum bending stress is there, and this is a channel section is there. And for the channel section, again, this is the bending stress diagram. You remember this sigma c, you might not be seen this clearly. Sigma c is the bending stress in compression, and sigma t is the bending stress in tension. So this is the diagram for the channel section, this is the diagram for the I section, and this is a rectangular section beam. This diagram is this. Next, moment of resistance. It is a very important term, moment of resistance. How to define the moment of resistance? It is a maximum bending moment resisted by the section. So whatever the section we have here seen, either rectangular, I section or channel section, how much maximum bending moment can resist? So that bending moment, maximum bending moment of the section is called as a moment of resistance. So it's very simple. In one line you can define this definition: maximum bending moment resisted by the section. And mathematically you can write, symbolically it is represented by m r. It is a moment of resistance is equal to, already we know, we derived this, m is equal to I by y is into sigma. So I is the moment of inertia, y is the distance from the neutral axis, maximum distance, and sigma is the bending stress in beam. So for this particular formula, I upon y, we know that this is the z we can write, and where z is the section modulus millimeter cube. So that unit of the section modulus is millimeter cube. So instead of the I upon y max, we can write z. So this moment of resistance formula becomes sigma into z. So what is that z? So that z is the section modulus, or it is also called as the modulus of section. So we'll define first of all this z, because we have written this z, I upon y max, instead we written the z. So let us see the definition. What is meant by z? Z is the section modulus. It is a ratio of moment of inertia. You can formula itself, you can write the definition. It is a ratio of moment of inertia of the cross section about neutral axis to the distance of extreme fiber from the neutral axis. So I have already talked that this I is the moment of inertia of the cross section, and y max is the distance from the extreme top fiber to neutral axis. That's why this is the y max, and it is a ratio I upon y, and that it is termed as z, section modulus, and it is denoted by z, and the unit of z or section modulus is millimeter cube, centimeter cube, and mathematically you can write the expression like this. So this z is equal to I upon y. For a symmetrical section, if the section is symmetrical about the neutral axis, at that time your sigma is same. Sigma c means bending stress in compression, sigma t is the bending stress in tension. So that both of these compressive stress and tensile stress are equal if the section is symmetrical about the neutral axis, right? Like this, you can see this particular section is symmetrical. So in this case, there sigma c and sigma t are equal values. And for unsymmetrical section, this sigma c will not be equal to sigma t. So at that time also, moment of resistance about compression and moment of resistance in tensile tension, that will not be equal. Okay, if the stresses are not equal, then moment of resistance are also not equal in compression and in tension. Next, design criteria. The condition of strength or of design is mathematically the condition for the design, for the safe design. This is a criteria, it is important. So sigma t max or maximum stress in tension, it should be less than or equal to allowable stress. Means this sigma t allowable is the allowable stress in the tension side, and whatever our maximum stress is there, that should be less than that allowable in the tension side. And also sigma c maximum stress in compression should be less than or equal to sigma c allowable. So this is design criteria. Our maximum value either in tension or in compression should be less than the allowable value. So these are the allowable value. Our maximum value of the stress should be less than allowable value. Where sigma maximum stress in compression, how to determine that expression from the flexural formula is m upon I is equal to yt max. Yt max is the distance uh, from the tension side, from the neutral axis to the top fiber, and this can be used here for determine the sigma, that is a maximum stress in tension, maximum distance in tension side. So m upon I into yt into max. So you can write the maximum stress in tension. Like that, you can determine the maximum stress in compression. So same m, moment of resistance or maximum bending moment divided by moment of moment of inertia of that cross section, and yc max is the distance in the compression side up to the top fiber or bottom fiber. So yc max is the distance of the fiber, extreme fiber, we can say the extreme fiber either top or bottom, that's why extreme fiber from the neutral axis. So y, you remember distance of the extreme fiber from the neutral axis. So here it is in the compression side, this y is there, so y max, and yt is mentioned for the tension side, yt max. In general, sigma max, if you want to determine in general, sigma max is equal to m upon z. So in general, you can write this m upon z, and z is equal to, this is the section modulus, I upon y max. So in this way you can write this m upon z sigma max, that's maximum stress you can determine in general m upon z, and that z it is I divided by y max. So greater the value of z, greater will be the strength of the section. If that value of the z is maximum, at that time the strength of the section is also greater, right? So greater the value of z, greater will be the strength of the section. So in this way we have taken this bending stress diagram, and also the section modulus, this specification, and we can say the definition, and what is the importance of the section modulus while determining the maximum stress at the particular section. So we have completed this section modulus and as well as the bending stress diagram here. Thank you very much.